Hi guys, and welcome to my laboratory. We're doing science now. So materials and their properties. We've looked at all sorts of properties of materials. So we're going to look at the features of a scientific report today. Don't worry, you're going to get to do an investigation because you can't write a report without having done an investigation. So by the end of your session today, you should be able to answer all three of these questions. So can I explain the aim of my investigation? Can I give specific instructions of how to complete the investigation? Can I clearly show results and make a conclusion? Now, these are all skills we've practiced. So we've made predictions, we've shown our results, we have had a go at writing instructions. I know we've done them in class. So you guys should all know exactly how to do them. So as you move through TLAB and on to secondary school, you're becoming scientists. As you carry out each experiment, you will think more scientifically than ever before. To accompany that, you will need to write up your findings in the form of a proper written scientific report. Every scientist is used to writing reports in the same style. So we're going to use today's lesson to remind you of the key features of a scientific report and to help you write your own. So, aims, or the question. You need to tell your reader what you were trying to find out. Whether it's what bounces better, a tennis ball or a brick, or whether it's what flies better, a paper aeroplane or a scrunched up ball of paper. You need a question that your report sets out to answer. So if you think about the beginning of our lesson, I had 3 questions. They were all can I questions. So those are what we're going to try and answer in this lesson. So I could say this lesson is running like a report. I have my aims or my questions for the beginning, and I've told you what we're trying to do. So for example, to investigate what's the best size for a parachute canopy. How could we do it? We need a prediction. What do you think will happen? What are your expected results? For example, I think that the biggest canopy will fall the slowest. Going back to that just for 1 second, don't forget, you can use the knowledge you've already got in your prediction. We know from before Christmas that the bigger the object, the more air resistance it encounters, so it will fall more slowly. We know that if you make something smaller, so we did the experiment with the sheets of paper and the scrunched up balls of paper, and we found that our sheet of paper floated down a lot slower than the scrunched up ball of paper, which just dropped straight down. So we can use our previous learning to try and help us in our prediction, try and work out what we think is going to happen. We need apparatus. Now, apparatus is a fancy word for equipment. So we write our list of equipment we're going to need. So for example, a force meter when we were measuring forces, or we might need pulleys when we were using pulleys. So think about the equipment you're going to need. So the next parts of your report, they're going to tell someone else what they will need if they want to repeat the exact same experiment. They may want to test your ideas, make sure if your results are accurate. This idea is something, again, that we've talked about a lot in class, that we need to make sure that we keep the test as fair as possible. So by being able to use the same equipment, so if you need 1 pair of shoes, size 9, made by Nike, to test friction, for example, you need to put that in your report as your equipment list so that someone else can go and get the same shoe from the same company in the same size, and they can test your results to see if they're accurate. Remember, you should draw scientific diagrams, not sketches. So draw with a ruler. We want nice straight lines. We want nice, neat labels to say what we've got, where it goes, how it goes together. So my example here, I've done it nice and neatly. I've labeled it as well. So I'm going to use a bin liner for the canopy. I'm going to use 30 centimeter lengths of string, and I'm going to use a peg as a weight. So these are all things that I've got that someone can pick it up and say, right, I've got this. I've gone and got my bin line. I've got my string. I've got my weight. How do I put it together? So this drawing is going to tell your scientists who are coming to inspect your results how you got your results. So we need to tell them how many we need as well. So it's no good just saying a bin liner and this and this and this, when you might need more of them. So bin liners, 5 of those. String. It's no good saying 1 meter of string when you've got 9 30 centimeter lengths, because you won't get 9 30 centimeter lengths out of 1 meter of string. So you could say string, if you wanted to be really, really accurate, you could say string bought from Wilkinson's, and this is the name of the string that I'm using. So by doing that, you give the people that are investigating the same thing, that are trying your results out or inspecting your results, the same opportunities that you had. So it keeps it as a fair test. Some tape. There's lots of different types of tape. You have masking tape, sellotape, gaffer tape. You have washi tape, the nice pretty Japanese tape that's got lots of different colors on it. They all have different amounts of stickiness to them. So if you're using a particular type of tape, put it in your report so that the person that comes behind you, or you're going to get bored of me saying this, but I'm going to keep saying it, so that if someone comes along to investigate your results, they've got the same equipment that you used. A weight, a dolly peg, or a clothes peg. But if you use something else for your weight, make sure you put it in there. Don't just copy down what we've got. A stopwatch. You're going to need to time how long it takes to fall. Now, stopwatches should be fairly similar. Doesn't really matter where you get them from. Now, moving on. We've made our prediction. We've got the question we're trying to answer. Excuse me. I'll start again. We've got the question we're trying to answer. We've got our prediction. What do we think is going to happen? We've got our equipment. We're all ready to go. Hang on a minute. How are we going to do it? That's where the next bit comes in, our method. The method is, if you like, the recipe for how you're going to do your investigation. You're going to explain exactly what you plan to do in your experiment, or if you're writing this up afterwards, exactly what you did. This is important. You should also explain how you made sure that you carried out a fair test. What variables did you change? Which did you keep the same? So a variable is, ideally, in a scientific investigation, you have one variable. So if we think about the friction investigation we did before Christmas, the variable that changed was the surface we pulled the shoe across. We all used the same force meter. We had the same person pulling the force meter. We had the same person inspecting the force meter to read it, which meant we kept it as fair as possible. We had the number of things that were changing kept to the absolute minimum. So when you're doing your investigation, make sure you have 1, 2, at most 3 things that will change. Everything else you need to keep the same. In your method, you need to identify what your variables are, so what things change, and what you're keeping the same. So I will take you through an example of what my method's going to look like. First, measure and cut 5 squares from the bin liners. Each square should be a different size. So one's going to be 10 centimeters, one 20 centimeters, one 30 centimeters, one 40 centimeters, and one 50 centimeters. So this is the length of the edge of the bin liner. So that's the size of square we're going to cut. Next, using tape, attach 30 centimeters of string to each corner of the bin liner canopies. So remember, we've got a nice square piece of bin liner. Finding the corners will be nice and easy. Once complete, bring the 4 strings together on each parachute and tie a knot as close to the end as possible. Now, tying 4 pieces of string together into a knot could be quite difficult. So if you connect them in a different way, you might say, actually, I'm not going to use that. I'm going to wrap tape around them to hold the ends together. That would be in your version. So it's making sure that someone can follow behind you. It's all well and good having one method that looks amazing and says you did it one way, but actually you did it a different way. So you need to make sure your method matches what your investigation was. For testing, hook the peg weight onto each parachute in turn. Now, I'm going to make a criticism of this because I've made a mistake. I don't tell you where you hook the peg. I drew a nice diagram, but I didn't show how the peg was hooked. Now, a dolly peg has got 2 little legs. It looks like a dolly, so it sits like that. So the string will sit there. It will sit on top. I might say I'm going to hook the peg over the knot or the tape together ends of the string. So if I was going to go back and do this again, that's the change I would make there. Make sure you drop the parachutes from the same height in the same way. We've got experience doing that from when we did our air resistance with the bits of paper. So we can do that. We know we measured the height. So you might want to say, drop them from a height of and give a specific height. That way it makes it even better for your people coming behind to investigate your results and check actually you haven't had a completely strange set of results that don't match up with what actually will happen. Using a stopwatch, time each parachute drop. When do I start the stopwatch? So, as you drop the parachute, start the stopwatch. When the parachute lands, stop the stopwatch and record the time. We can add in more. The better detail we have in our investigation, the better able the people that follow behind us are able to come and check it again. For the test, we used the same material for our parachutes, the same lengths of string and the same weight. We also dropped from the same point. The only variable we changed was the size of the canopy, making the test fair. So we've addressed some of those comments as we've written our method. It's nice to have an extra paragraph just to say, this is what we did, this is how we did it, and this is what we found. Actually, no, we're not what we found, what we changed. My mistake there. And identify what the variable was. So in our parachutes investigation, it's the size of the canopy. If we were investigating something else, then we'd think, what's the one thing we changed? So going back to the example of our friction experiment, what we changed was the surface we pulled the shoe across. Everything else was kept the same. Our results. So this is why we do the investigation. We're trying to find something out. So as you carry out your experiment, you'll need to keep a record of what happens and what you measure. We use tables for some of them. We just had rough notes on some of the investigations that we did. And often, as I said, it will be a table, nice and easy to fill out. Something like this. So say the size of the canopy for our example experiment, how long it took to fall a certain distance before it touched the ground. And then from this, I can use that data. I've generated my data. Now, what you could do, if you wanted to be super, super scientific, you could do this 3 times for each one. That will give you a set of results that you can then quickly and easily find out whether your results are accurate and whether they're repeatable. It might be the case that something really strange has happened. For example, if we look at the 50 centimeter one, it's fallen much faster than the 40 centimeter one. Now, If for some unknown reason I decided to drop my parachute upside down for the 40 centimeter one and I dropped it the right way up for the 50 centimeter one, that would mean I've done something wrong. So it's worth checking experiments. If I was doing this one, I'd go back and drop the 50 centimeter one again, just to find out whether I'd done something differently by mistake. So look at your results as you get them. You'll find sometimes that there'll be little mistakes in there that you need to go back and just re-examine. Our conclusion. So this is what brings our investigation together. This is where you must try to explain what you found out from your experiment. Don't just write what happened. I found out that this happened. It doesn't really explain your thought process behind why you think it happened. For example, in testing, the 40 centimeter canopy fell the slowest. The larger canopy was unable to open in time. I believe that the best size of the parachute canopy depends on the weight you attach. So the bigger the weight, the faster it will fall. The bigger the canopy, the more air resistance it will encounter, so it should slow it down. Obviously, there's a perfect size before the canopy gets so big, as in the investigation here, that the canopy doesn't have the time to open. Or in the case here, our minion flying through the air. So now over to you. Your task. I'm going to give you a choice of 3 investigations. So think about what you've got at home. And I'd like you to choose one of the following questions to investigate. First one is, how should I fold a piece of paper to throw it the furthest? So you could fold it into quarters, into eighths. You could fold it into a paper aeroplane, something like that. What liquid is best to clean a penny? Now, I've heard, if you've got some, tomato sauce works really well. You might find something else that works even better, but a liquid, so something you can soak your penny in. What shape of pasta is the strongest? Not quite sure how you would go about investigating it, whether you'd weigh something down on top of it until it's squished, whether you'd balance it between 2 books and have a gap in the middle and put weights on top of it until it snaps. That would be your investigation and your method. So, warning, please don't throw the bits of paper at anyone. I don't want reports of people getting poked in the eye with a paper aeroplane. With your liquid for cleaning the penny, be careful. Some cleaning products can be quite dangerous to your skin, so you will need some adult supervision for this one. And the pasta one, please don't steal it off someone's plate. They won't be very happy, and cooked pasta probably won't be the strongest thing to investigate. But that could be one of your variables. Is cooked pasta stronger than uncooked pasta? So, write your report. Choose your question. Make sure you include your aim, what you're trying to find out, a prediction, what you think will happen, the apparatus, the equipment that you're going to use, the method, how are you going to do it, your results. Can't do an investigation without the results, and your conclusion, and see if you can explain why that happened. So why what happened in your investigation did. Right. Good luck, scientists. I look forward to seeing your investigations on Tapestry. As always, take care, stay safe, and we'll see you again very soon.